Uh, hi guys. This is Srikkanth here. Today I'll be in this session. I'll go over the solution of Inversion Mod 2 from the recent long challenge, October long challenge on CodeChef. Before I get to the problem, I just like to quickly remind you about the subscription program that CodeChef launched recently in collaboration with an academy. Uh, so this is a program, a course. You get access to courses that are taught by the best educators in computer programming, the best people in computer programming. So we have there are IOI medalists, ICPC World finalists, etc., and engineers from Google, Flipkart, and so on. So these are like very good people who are, I would say, the best people, and they will be you get to interact with them in live sessions, and then you get access to courses that are created for you, and you get practice problems and practice contests as well. And you also have dedicated discussion forums and Discord servers where TAs and educators will be answering your doubts, and so on. So the subscription program starts at about 2K per month, and uh, yeah, you can go through it and check it out uh, to see if it's for you. And um, that's it about the subscription program. So coming back to the problem. So uh, okay, so the problem statement is simple. Uh, Find the number of permutations of one to first n numbers, the number of permutations of these n numbers that have exactly k inversions, modulo 2. Okay, so I mean, essentially what you want to find is the number even or odd, okay, equivalent to modulo 2. But yeah, so there are n factorial permutations, and how many of them have exactly k inversions. So an inversion is a pair that is not correctly sorted. So uh, a pair I comma j is an inversion if I is less than j and ai is greater than aj. So let's consider that 3, 2, 1, 4. So the pair 3, 2 is an inversion, 3, 1 is an inversion, 3, 4 is not an inversion because 3 comes before 4 and uh, in the sorted order and in the permutation as well. So every pair that is in the right order relatively uh, is not an inversion, and every pair that's not in the right order is an inversion, right? So 2 comma 1 is another inversion. So there are 3 inversions in this permutation of sense 4. So you want to find the number of permutations that have exactly k inversions. Okay, so it's a essentially it's a counting problem, right? Uh, let's come back to the modulo 2 a bit later, but for now we will focus on finding the exact value and how to write a program that can count this. Okay, so the brute force way is to just find all permutations and count the inversions, but that's not going to be feasible for even uh, small values. Okay, and here the constraints we have is n is 10 power 10. Okay, so n is very huge. Uh, So essentially, let's call this number as f of n comma k. Okay. The number of permutations of the number from 1 to n, and having exactly k inversions. Okay, and there's another constraint that k is within 0 and n. This is important. But the number of inversions generally need not be less than n. It could be n squared also. Like for example, a completely descending. For this example, the number of inversions is 3 plus 2 plus 1 because every pair is an inversion. So you could have n squared inversion in worst case, but in this problem we only want or the constraints are that k is less than n, which we will see is very important to get an optimized solution. Um, right. So the actual solution for this problem is that there exists a formula that you can uh, find by googling, etc. Today, what I'm going to be doing is I'm going to be giving you like sort of a derivation of the formula, and the problem just amounts to implementing the formula in a simple C program. Okay. But let's start from scratch. Okay. If I want to evaluate f of n comma k, how would I do it? So one common way uh, to uh, to solve such counting problems is to find recurrence relations. Okay, uh, this is very common. Uh, so how do I count f of n comma k? Can you break down this problem into subproblems? Okay. And once you have a recurrence relation, you can compute it quickly using dynamic programming or uh, usually dynamic programming. Okay, so let's start with counting the number of permutations. Okay, let's see. Let's ask the question: what the first element is. Okay, so the idea. What is the first element? Okay, so the idea is we have an Orion size, and is it possible to fix the first element and treat the n minus 1 separately as a subproblem so that we can get recurrence relations for this. Is it possible? Okay. So let's say the first element is 1. If the first element is 1, then this element will not contribute, or this element will not be it will not contribute to any inversion because everything to the right is greater than it, right? In the correct order. If the first element was 2, okay, so 1 will occur somewhere, right, in the permutation in the amongst these n minus 1 values. So this will give this particular, the first element will be responsible for uh, exactly 1 inversion, okay, and all other inversions will be uh, among pairs within these n minus 1 numbers. Okay, so we can treat them as a separate permutation, and this element 2 is responsible for exactly 1 inversion, regardless of what the order is among these n minus 1 elements. Okay, so this is the subproblem that we'll be breaking into. Okay, and similarly, if you have 3, then you'll get exactly 2 inversions. Okay, because 1 and 2 will be present somewhere in the array, the last n minus 1 positions. So that will give you 2 inversions that 3 is responsible for, and all other inversions will be among pairs here. So if the first element is x, okay, so then you get x minus 1 inversions from the first index, okay, and all other inversions in the array, if any, will be present in the last n minus 1, among the last n minus 1 elements in the array, okay. Right. So if the first element is x, right, the remaining n minus ones are not a permutation from 1 to n, right? Because our problem was permutations from 1 to n, and k inversions, right? We wanted, we had the idea now is to see if we can get, if you can use the subproblem for n minus 1, for permutations of size n minus 1 to calculate the answer for size n, right? But if we fix the first element to be x, okay, so x will not be present in the subsequent n minus 1 elements, but the n minus 1 elements will be distinct, okay? And now I'd like to again, yeah, that the only the relative values determine the count of inversions, okay? What does this mean? So suppose I had an array with 0, 1, 2, and so on to n minus 1, okay? If I add 1 to every element and make it from 1 to and so on to n, right, the inversions are not going to change. So if I had a permutation of from which contained values 0 to n minus 1, and if I add 1 to each corresponding element to get a permutation from 1 to n, those the inversions aren't going to change, right? Like for example, I have 0, 3 to 1, and then I had 4, sorry, 1, 4, 3, 2. Both of these have exactly the same set of inversions, right? So it's not really about the value, but the relative value. Okay, so as long as the numbers are distinct, we can consider any set of n distinct numbers to be a permutation. Okay, or there will be an equivalent permutation that has the same set of inversions, right? So for example, if I have the array 1, 5, 4, 3, right? This the set of inversions or the pairs that contribute to my inversion will be same as the set 1, 2, 3, 4, right? So 1 was the least element, 3 was the second least element, 4 was the third least element, 5 5 was the fourth least element, right? So only the position in the sorted order determine the the set of inversions. So once we fix the first value, right, we can treat this as a permutation of size n minus 1, from which we need, so we already have x minus 1 inversions in the first element. If this array has to have k inversions, we need k minus x minus 1 inversions from a permutation of size n minus 1. Okay, so that gives us the following recurrence. So if the first element is 1, then essentially what we have is a permutation of size n minus 1 with k inversions. If I have the first element is 2, then I have a permutation of size n minus 1, but k minus 1 inversions. and so on up to n. Okay, so every permutation of size n will fall in one of these categories. Okay, so f of n comma k must be f of n minus 1 comma k plus f of n minus 1 k minus 1 plus and so on to f of n minus 1 comma k minus of n minus 1. Okay, so this is the recurrence relation for f that we can get by breaking down the problem into subproblems. Okay, and by fixing what the first element is. You can also fix what the last element is. You'll get the same, similar recurrence relations. And then let's talk about the base case. The base case is f of 1 comma k is 1 if k equals to 0 and 0 otherwise. So for size 1, you have just one element, this array, and it has 0 inversions. So f of 1 comma 0 will be 1. And for all other k, there are no permutations of size 1 to have those many inversions. So we know f of 1 comma k, and we can get f of n comma k from f of n minus 1 comma k from these values. Okay. So we can implement this using dynamic programming or just a recurrence relation. Just memorize the values and you can write recursive functions that calculate this. So say GP of n of k is simply some, this recurrence relation. X is the first element permutation. You can get this, right? If you implement this as is, it'll be, I guess, n squared k, because for each, I would say n k squared, because you can say x is minimum of 1 comma k. So if the complexity is in k squared, if you just implement this as is, but you can see that this is a perfect sum, right? Or this is a subarray sum of GP of n comma k is a 2D array. If you think of this as a 2D array, GP of n minus 1 is a 1D array, and this summation is a subarray sum of that array. So by maintaining perfect sums, we can get O of nk, which I guess gets you some points via subtasks. Okay. Right. So to optimize this further, we're going to be needing generating functions. Okay. So generating functions are a popular method for obtaining formulas for combinatorial problems like this one. And it also helps you find formulas from their recurrence relations. Okay, so here we have a recurrence relation. Like so, but the recurrence relation can only do so much in terms of code complexity. So we would like an explicit formula. Okay, and what a generating function is. So a generating function is a polynomial that represents a sequence. Okay. Essentially, what we are doing is we are visualizing the sequence as a polynomial. Okay, and that helps us use some algebra to find useful formula. Okay, as we will do here. Okay, we will be doing exactly that. Okay, so for a sequence a1, let's say a0, a1, so on. It could be finite, it could be infinite. Doesn't matter. the recurrence the generating function for the sequence is simple. Sequence AI explorer, or it's just a0 plus a1x plus a2x squared plus and so on. Okay, if this could be an infinite sum as well. So this is the generating function that's defined for that's associated with a sequence. Okay, let's use this. So let's think about the sequence f of n comma 0, of n comma 1, and so on. Okay, n comma n, and even after that. Okay, so this is a sequence, right, that we would like to find, and the associated generating function for this sequence is very simple: 0, 1x, 1. So writing it like so, and I'll give it a capital F. Okay, and let me write infinity. Okay, so let me write infinity here, and we can define f of n comma anything greater than nc2 as 0. So although this has, I'm writing infinite terms here, there are only finite positive terms for f. Okay, so but it's not important, like it need not be finite as well in any case. So we would like to find f as a polynomial. Okay, so often for sequences like this, f is can be represented as a nice polynomial. Okay, so we'll try to find that out, and we can find that by using the recurrence relation here. Okay, so let me just write down those steps of how to find out f from a given recurrence relation. Okay, so let's start by writing down the recurrence relation. Okay, n minus okay. One to minus 1. Okay, and multiply both sides by x power k. Okay, so okay, 2x power k equals minus 1 k x power k. Okay, and I would like to obtain a neat formula for fn. Okay, so I will try to incorporate fn here. So I would like it to be like so, into x. Okay, and similarly, k minus 2 into x squared plus and so on. Okay, let me write it like this. X power k minus 1 to x power n minus 1. Okay, so by multiplying both sides by x power k, this is what you get. Cool. Let's yeah, if we do summation both sides from k equal to 0 to infinity, we can get fn on the left hand side. What about the right hand side? Let's see what happens there. Summation k equals to infinity, which of n comma k x power k equals summation infinity of this thing. But let me split it up like so. Okay, plus summation minus 1 into x plus and so on. M minus 1, okay, minus 1 to x bar minus 1 into x bar minus 1. Okay, so this term is fn. Okay, this term is fn minus 1. This term is also fn minus 1, right? Because notice, yeah, k equal to 0 to infinity, right? For k equal to 0, m minus 1 comma minus 1 is 0, right? So there's no so we can define it like this: f of n comma k is 0 if k is greater than nc2 and if k is less than 0. So these cases don't really make sense, right? So the number of permutations is clearly 0. So going by these definitions, right, k equal to in this case, k equal to 0, the term will just contribute 0, right? So we can equally write this k equal to 1, or write k equal to 0 to infinity and replace this by k here. Okay, so the infinite summation doesn't change. Okay, although we have shifted it by 1, right, by bringing x bar k minus 1 inside here like so. Because it's an infinite sum, this also is fn minus 1, right? In all other terms, this guy is also fn minus 1. Okay, so essentially what this is fn sorry about that. Right, fn equals fn minus 1 plus fn minus 1x plus fn minus 1x squared plus and so on, fn minus 1 x bar minus 1. So fn is fn minus 1 to 1 plus x squared plus and so on to x bar minus 1. Okay, this is an easier reconciliation, right, from the earlier one that we had. Okay, so we can simplify, we can repeatedly apply this further. So you can get fn minus 2 to 1 plus 2 to, okay. And if you keep applying this, we know that f1 is 1. Okay, because remember f of 1 comma k is 1 if k equals to 0 and 0 otherwise. So capital F1 will be sigma f of 1 comma k x bar k, and sigma f1 comma k x bar k, and except k equals 0, everything else is 0. So you get this is equal to 1. Okay, so by putting this in, you get fn equals 1 to 1 plus x to 1 plus x squared into and so on till 1 plus x squared so on to x bar minus 1. Okay, so we now have like a good we now have fn, right, expressed in terms of polynomials that we know. Okay, it's very convenient. Okay, and I'd like to remind you that this is equal to f of n comma k x bar k equal to 0 to infinity. So f of n comma k is actually the coefficient of x bar k in this expansion. So all we have to do is find the coefficient of x bar k. Somehow we can use algebra here to find the coefficient of x bar k, which we will do. It won't be so simple in this case, but usually in other recurrence relations, you can get a nice formula for the recurrence by converting it into generating functions. And writing out the polynomials like so. Okay, yeah, so this is, now we have to find the coefficient of x bar k here. And let's write the geometric progression, let's reduce the summations here into simpler terms. So this will be x minus 1 by x minus 1 to x squared minus 1 by x minus 1, x cubed minus 1 by x minus 1, so on to x squared minus 1 by x minus 1. Okay, so that is x minus 1 to x squared minus 1, so on to x squared n minus 1 into x minus 1 power minus n. Okay, so you should know power series of common functions. So this is summation n plus k minus 1 choose k x bar k k equal to 0 to infinity. Ouch. Sorry about that. Yeah, so 0 to infinity. Okay, this term is equal to this. This term is a bit harder. Okay, it's called there's a theorem from Euler. It's called Euler's pentagonal number theorem. And this expression is actually summation j equals to 0 infinity minus 1 power j into x power 3j to j plus 1 by 2 plus x power 3j into 3j minus 1 by 2. So this is not a trivial result. Like this is yeah, a very tricky theorem. But if you can find this by Googling, etc. There's a nice proof for this theorem that I'd like to outline briefly for you for the lack of time. So essentially, if you think about expanding this, right? If you do the algebraic expansion of this, what terms will you get? You would get some. So you have x bar 1, x bar 2, x bar 3, it's on to x bar n, right? So for each term, you either choose the x term or you choose the constant term, right? So if you choose a number of terms, you'll have a minus 1. You'll have a multiplied your term will be negative, and if you choose an even number of 1 terms, your term will be positive, right? So what we can think of this we can think of this as a sum. So x power a subset of 1 to n, right? Because for some of these terms you will choose the x term, for some of these terms we'll choose the constant term. So essentially this is sum of x power sum of a subset of n. Okay, so for any subset we get a corresponding term, x bar 3 times x bar 1 times x bar n, etc., times minus 1 power size of the subset. Okay, so if the subset is odd, then the term will be negative, otherwise it will be positive. Okay, so this is essentially that. And if we want to find coefficient of x bar k, a quotient of x power t, let's say, of this expression. Okay, let me write it down instead. Okay, so if we want to find coefficient of x bar k here, it is nothing but the number of odd subsets or number of even subsets that have some k minus number of odd subsets. that have some k, right? Because every subset sum will contribute to the expansion, and the coefficient or the power of x in that term would be the sum of the numbers in the subset, and it would, if the size is odd, then it will be negative, so you'll be subtracting one, and if the size is even, you'll be adding one. Okay, and it turns out like for almost all subsets you can find that they are paired up. Okay, so subset sums are almost equally distributed among odd and even elements. Okay, so essentially what I mean by almost is that a lot of these terms are zero, meaning that for most k, for most exponents, the number of even subsets that have that particular sum is equivalent to the number of odd subsets that have the sum. Okay, and how do you show this? So there's a nice way to show this, and you can read more about this online. So let's say I have a subset sum that evaluates to let's consider this following subset sum, right? That's even length, and that's adds up to 22 may not be a good yeah, so 22 is a good number. Okay, if you, what we want to do is we want to show that that difference is zero for most numbers. If we write this in this form, what I'm doing here is I'm writing each number in the row and writing the numbers in descending order, the subset elements in descending order, and associating with each, let's say, an object, like so, and visualize this sum in a grid like so. Okay, so 7 plus 6 plus 5 plus 4. Okay, yeah, this was a bad example. Let's say 7 plus 2 instead. Okay, so what I can do is corresponding to this sum. So what I can do is I can rearrange these beats amongst these rows to create alternate sums. Okay, so let me remove these rows and get 7, 8, 3, 4, 5, 6. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7, 8. Okay, and this is remains 5. Okay, so this is 8 plus 7 plus 5, which is again 7 plus 6 plus 5, this is 20. Okay, so 8 plus 7 plus 5 is also 20. Okay, what I did was redistributing these objects into these rows gives you other subsets that also give you the same sum, 20. Okay, so what I did was I repositioned these two beats to here. Okay, so I took the last row, I arranged them in descending order, took the least row and distributed them amongst the highest rows. Okay, and I can do it back for. Okay, so notice what I did was this is a subset with four elements, and by removing the last row and rearranging them here, I got a subset with odd number of elements. Okay, so the idea is that we can rearrange these beads from here to here so that the number of odd equals the number of even. in most cases. So I'm leaving some stuff for you there because due to lack of time, but you can look up the proof online. uh, it's very interesting. So I will just briefly say, or shortly say, that the method is we take all the elements in the last row, the smallest row, and distribute it amongst the highest elements. Okay, and if you're not able to do that, like in this case, the last row has too many elements, right? And we cannot distribute them amongst the uh, previous rows. In this case, we can do the opposite. We can take one element from the uh, biggest rows, and we can put them as a new row. Okay, so essentially, what we're doing is we are removing all the objects in one row and redistributing them into the other rows. This converts the parity of the subset. So a subset with even sum is converted to a subset with even number of elements is converted to a subset with odd number of elements, and they have the same subset sum. Okay, so this procedure, uh, if you can formally define it, you will find that you will not be able to do this procedure for numbers that are completely descending like so. Okay, so for these numbers, what will happen is you cannot remove all the four numbers and distribute them amongst the higher numbers so that the order is still satisfied, and you can't take one from each and add it to the or create a new row. Like, so in this case, uh, that is not possible, right? Without disturbing the order of the element. So if you were to subtract one from each row here, you would get two equal elements, right? So in cases like this, you will not be able to find corresponding order even elements, and those are the terms that end up having a non-zero value here. Uh, yeah. So those are the coefficients that for which this expression will not be zero. And those expressions are essentially numbers of this form. So numbers like k. Okay, so in this case, we can do that. Let me give you an example. Okay, numbers like so, which have k plus 1 plus k plus 2, so on to k minus 1. So numbers for numbers that have this sort of configuration, you will not, for this particular partition subset, you will not be able to find a corresponding even or odd subset. And so this sum is k by 2 into 3k minus 1. That's the term that appears here. And the other term is plus 2k. This is one of the terms. The other term is k plus 1 2k, which is essentially sorry, k by 2 into sorry, plus 2k minus 2. So sums like so, which is k plus k plus 1 up to 2k minus 2 and up to 2k minus 1. These numbers won't be will only have non-zero terms in the expansion. So this will evaluate to 3k minus 2, I believe. So these terms are the terms that will be positive here, and so you get this identity. Okay, you get this identity. Okay, so plug in this expression here, and then we know how to expand this, so we can find fn. You can find a formula for fn, sigma minus 1 for j x bar 3j into j minus 1 by 2 plus 3j into j plus 1 by 2 times, again, j is from 1 to infinity, and here you have n plus k minus 1, choose k, x bar k equal to 0 to infinity. Let's we use a different variable here, s. Okay. And we have to find coefficient of x bar k in this expansion, right? So the curious thing here is that you can take a term here and you can take a term here and you can multiply both of them to get the coefficient of x bar k. So the interesting fact is the terms that we are concerned about here are those terms with powers less than k, less than or equal to k, because powers with which have this value greater than k will not contribute to the coefficient of x bar k, right? Because the corresponding term here will be positive. So if you have like x bar k plus 1 here, you cannot multiply it with anything here to get x bar k. So essentially what we're doing is we're visiting each term here and finding the corresponding term here, which will give you a coefficient of x bar k, and multiply them to your result. Okay, so wait, how many values of k in this expression, or how many exponents are here that are less than k? Okay, so we have 3j into j plus 1 by 2, and we want this to be less than or equal to k. We are concerned only about those elements, and for each of those elements we will search for k minus 3j into j plus 1 by 2 over here. Okay, and we will look for that term here and add them up. Okay, so we'll look for coefficient of x bar k minus 3j into the j plus 1 by 2 here. Then we will look for the coefficient of there should be a minus 1 for s here, I believe. Yeah, so look for the corresponding coefficient here, multiply them, and get the coefficient of x bar k in the entire expansion without explicitly expanding it. Okay, and how many terms are here? Because 3j into j plus 1 must be less than or equal to k. We have j is approximately square root of k. Okay, so some 2 by 3 square root of k. So j is of the order square root of k. Right, so there are only square root of k terms here that we care about, and we can get all those terms, right? They are just minus 1 power j. 3j into j plus 1 by 2 are the terms here, and their coefficients is just minus 1 power j. And for each of them, we can get the corresponding coefficient in this sum that adds to k and get the answer. So in O of square root of k, so there are O of square root of n choose p terms. Let me write as m choose p terms that we have to talk the square order of square root of k binomial coefficients that we have to calculate in our answer. And that's the optimization that gives you 100 points in the problem. Okay. So let me explicitly write down the formula here. N plus k minus 1 choose k plus sigma j equal to 1 to infinity, and plus k minus 3j into j plus 1 2 j minus 1 by 2, choose equals k minus 1 minus this, k minus j into j minus 1 by 2, and then plus for the other term as well. N plus k minus 1 minus 3j to j plus 1 by 2. K minus 3j into j plus 1 by 2. Okay. So there are only square root of n plus k terms here that we will be bothered with that for our summation, and sorry, square root of k. We have k minus square root of k terms here, and we will just evaluate each of them modulo 2. So now NCR modulo 2 is all we need, and NCR modulo 2 is actually very interesting. You can get this in log r by finding the number of exponents of 2, the power of 2 in n factorial, finding the power of 2 in r factorial and n minus r factorial, and you can do that and get NCR mod 2. But there's an easier way to do this that I like to point out using Lucas theorem. So Lucas theorem says and choose r modulo p is equal to n0 r0 into n1 r1 so on to nk rk modulo p, where n0, n1, and nk are the digits of n comma r in base p. So convert n to base p, convert r to base p. That will be n0 p0, sorry, n0 p plus n1 p power 1 plus and so on. And similarly, r equal to r0 0 plus r1 1 plus and so on. If you write convert n and r to base p, and you have these digits, n choose r modulo p is equal to n0 c r0 into n1 c r1. So if you apply Lucas theorem, it's very obvious that these are just in the binary representation. These are just ones and zeros, right? And so here you have 0 choose 1 is 0. So if you have a bit in n and if you have a bit in k, if you have a bit in n that is 0 and the corresponding bit in k is 1, then this product will be 0. Otherwise, the product will be 1 because 1 choose 1 0 and 1 choose 1 are both 1. Okay, so as long as for every bit in 0, for every bit that is 0 in n, the corresponding bit in k must also be 0. If that happens, then the NCR mod p modulo 2 is 1, otherwise it's 0. So this is equivalent to saying that k must be a subset of n. So r must be a subset of n. So NCR modulo 2 is actually equivalent to n and k equal to k. So in O of 1, you can get NCR mod 2. And in O of square root of k, you can solve the whole problem, which is enough to get 100 points. Yeah, and but the crucial part of this problem was finding this formula, which was available online. But I hope like I gave you some intuition about generating functions that are useful in combinatorial problems like this to get an explicit formula like this one. Like this one, instead of, and this speeds up the dynamic programming, a simple dynamic programming solution for the recurrence relation. Okay. In this case, finding out the polynomial was hard, but usually because it involved this Euler's pentagonal theorem here, but usually for other recurrence relation, it's much easier to find these polynomials. Like usually you have x minus 1 power minus 1 and so on in problems like so. and you can get this closed form expression much quicker, much more easily than this. So that's about it for this problem. Thank you for listening.